Hi, welcome back, everyone. Today we want to finish our system and software security discussion module because next class is a guest lecture from Salman, and from next week we'll talk about a different subject, cryptography. A little bit recap from last class. We talked about rootkit, ways of analyze code, repackaged apps. And we mentioned hardware security. In particular, we use Intel SGX, the software guard extensions to describe how to realize the trusted display. If you have a compromised browser, compromised system at the same time, how would you do online shopping? Okay, and so it's different ways for you to see how you can come up with security solutions under stronger and stronger threat models. And of course, the other solutions that involve compromised OS is considered a very strong threat model. Usually we trust OS. For those of you who are still looking for class project, I want to mention my project, Crypto Guard from our group. It's a Java crypto API misuse detection. It's a static analysis, code screening. We don't run code. We use existing tools to design algorithm to detect constant password, constant secrets, return true in certificate verification, and catch exceptions in certificate verification, various kinds of security and cryptographic related coding errors. And so if you're interested, visit our website and learn more and think about different ways of contributing to make this more accessible, more usable. And of course, if you decided to do it, let us know. We can give you more insights. And so system security, we talked about this problem before, and I want to revisit a little bit now. How do you make sure your OS files are not tampered with, or any files on your systems? And OS files, they're considered the foundation of your system, so very important. Before we talked about Tripwire, a system's integrity solution. It's very classic, very simple in the sense you just compare digest. In this case, it's cryptographic hash of files. One file, one hash, and then if a hash matches, that means that the file has not been changed. However, we mentioned that it has some issues. And then first of all, recall that the basic steps are for Bob to compute a whole bunch of digests before everything starts, right? So this is the clean version of digest. And then hopefully all these hash values are stored in a safe place. And every morning Bob enters his office not knowing what had happened the night before. And so Bob recomputes the hash values of all the OS files and then see if anything changes. If nothing changes, then the OS is intact. But then we said that the threat model of this tripwire solution is very limited because the adversary, we assume it cannot corrupt the digest database, cannot tamper with the digest computation. But then in the meantime, we assume the OS may be compromised. And so there's some contradiction here. On one hand, we trust the OS. On the other hand, because we trust the OS to store the hashes, to do the hash computation. On the other hand, that we assume that the system could be hopelessly corrupted. And so the problem is we need a solution, a new solution, or a modified, improved solution to address a more realistic threat model, which is stronger. This stronger, more realistic adversary model would assume the attacker will be able to correct both the database and the digest computation. And of course, we cannot just do everything on this one computer. And so we need external help. right? So what are the external help? Bring in a remote trusted server. And so a remote server can store the database. And then we can assume that the database is safe there. And so that's a good idea, right? So we have a remote server, and think of the scenario where you have a big company, and now during COVID, the employee can work from home, but then the company has a policy. Anyone want to connect to the company network, access internal files, so will be able to prove to us that the employee's computer is intact, has high integrity, has not been compromised, is running a clean version of OS. And so we can have the employee send a whole bunch of OS hashes, and then the server checks. So that's much better than the previous solution, right? So you don't worry about the database being corrupted. But however, we still have issues. The adversary may still tamper with the digest computation because that's done on the employee's computer. What if the calculator in the program would refuse to compute? Instead, it would just say, hey, this is the hash, just to use this, right? So then in that case, this is more complicated. We cannot just solve using software only solution, right? Because we assume the software is broken, and it's gonna be difficult to say, okay, this part of software is not broken, this part of software is broken. So a better solution would involve hardware in a hardware-based trusted execution environment, commonly known as TEE now. Last time we talked about TPM, SGX will be able to do this operation. The TPM can do the computation, hash value computation, and then make sure that the values are not corrupted, and then bundle them up and encrypt it to the server. And this is exactly the solution. In the stronger threat model, how would you verify the integrity of OS? A lot more complicated than we have seen before, right? So you have the step one is to have remote server get a copy of the clean digest. Step two is to have the TPM does the computation and collect the hash values, encrypt them, and send it over to the server. If we have time at the end of the semester, we'll look more into how these operations gets done, because there is keys involved, the certificate involved, signature involved. But I want you to understand that you see that weak threat model, you have a simpler solution. Stronger threat model, you have more complicated solution, but there's almost always you'll be able to find a solution as long as you have an additional helper, either an external server or a hardware. And so it's definitely doable. And by the way, for those of you who are interested, this is the architecture of this chip, TPM chip. It has, computation ability, storage ability, and then it's really small, inexpensive. So that's for file system integrity. I want to start very quickly on OS security. OS security is something that conceptually is relatively simple. And the discussion will mostly cover a lot of history, in the old times. Well, how do people secure operating system? What are the goals of OS security? And of course, the currently the most common one is, of course, is Linux OS used in many commercial and sort of production environments. It's based a lot on Unix, and Unix based a lot of on Multics. Multics is when it started back in the 60s, a long time ago, where the computers would the computers probably still do punch card. It's just a gigantic, like a big room size computers, and then you want to, and it's mostly managed timeshares. Timeshare is where you have like the whole town or Blacksburg probably only have one computer, and then all the users, the student, faculty will share it. And so you have multiple processes, files, and make sure that the access control, the authorization is done so nobody is overwriting other people's files, right? So login, password, and protection ring, and so you have more internal kernel, and then external, the user has lower privileges. So all these concepts came from them. Another important, so a lot of times that you will see people talk about multi-X. DoD had for a long time this Orange Book, which is started as a description of standards for evaluating computer security solutions. One way of calling the solution is computer security controls, and you see a lot of places it's control, it just defense. If you sell solutions to DoD, they will use the Orange Book as a recipe to evaluate, to assess how good your solution is. And so nowadays, you almost don't hear people mentioning Orange Book. When I went to grad school, I still occasionally met people who say the Orange Book said, and so you're like, okay, what is this Orange Book? Memory protection, we talked a lot about non-executable stack, right? So we said that the stack would only just have a writable permission instead of writable and executable. And so there's this attack architecture from IBM back in the 70s and 80s. It has a 33-bit instructions. And so the 33rd bit is for indicating additional permission values. And of course, you don't have to stop at 1 extra bit. You can have 2 extra bits, 3 extra bits. And so the machine is made to be able to recognize these additional bits. Therefore, that you will be able to have really fine-grained memory protection. You see, this instruction has read access. That instruction has a read-write. And so it's extremely fine-grained at the instruction level. And of course, will be compatibility issues if everybody else are not using this, and then the code written for this architecture would not be executed on other machines. But this just shows that if you work hard, you will also be able to have like very fine-grained memory protection. Multi-level security, this is a very simple concept. You just have different levels of secrecy, okay? And then you can use these labels to mark subjects. That means person, user, or objects, that means files. And then there's this concept called compartment, and you can think of this as topics. And so, for example, this file may be related to, say, fuel cell energy, and then maybe related to medical devices, and so across multiple topics. And then the person may be working on multiple projects, and then we'll have these different labels as well. Person would also have secrecy labels. I may be, I have top secret clearance or classified clearance. And so based on this setup, this multi-level security setup, you can define policies. And then a lot of times, when this computer security this field started, a lot of times was for DoD military applications. Nobody talks about usability, okay? Everyone will talk about the toughest policies. And one of them would be need to know policy. That is, if you don't work on a particular project, then you don't have to know it. And if you have to know this project, then you only be able to access files when you clearance is larger or equal to the file's clearance. So we call it a dominance relationship. The subject has to dominate object. So top secret, person can read the top secret, secret, classified, unclassified. But then if you only have a classified clearance, then you won't be able to read the secret and top secret, right? So it's very, very intuitive and also very, it makes a lot of sense. Here's some more formal notation, and there's this compartments has to be a superset or equal to the compartments of the subjects. That this is just shows that you have to work on a particular project in order to know it. You know, if say you have top secret clearance on nuclear weapons, but you don't have top secret clearance on medical devices, then you don't have the access. And again, need to know, strictly need to know, very rigid. Under that kind of concept, there are very popular at that time, back in the 80s, very popular confidentiality model. And this is for access control, authorization, who can access what. And so one model called the Bell-Abdullah, BLP for short, and this should be distinguished from the BLT in the sandwich universe. And BLP says that we can allow people to read lower security level objects, okay? So like we just talked about, that makes sense. BLP would also specify that when you write something, like when you submit files, when you enter new information, you can only enter information to an upper level objects. Okay, so in this means that if you enter a file, you cannot have the ability of a top secret person write an unclassified file. That would be bad because the top secret person may accidentally reveal information in an unclassified file and end up having a clear Alice in this example be able to access it. So in order to understand this, it's very important to remember this is a confidentiality model. The whole goal is to keep things secret to the maximum. Everybody has a label, every object has a label. Information only goes upward. See this object, this figure, information, read, write, go upward, okay? You and only when you so let's give an example, okay? If you read, subject can read object 1 because it's the same level, subject subject can also write to a higher level. If no read access, I'm thinking that this figure may not be, has some issues. Okay. So here is the BLP model with more descriptions. Information flows up, not down. Okay, when you submit information, when you write information, creating new files, all the information leads to having higher authorities be able to view. But high people with higher clearance won't be able to generate files for lower people to view, and for fearing that they leak sensitive information. And here is more notations about different policies under the BLP model. BLP model also has another theorem, which is also very intuitive. Basically, if you have this write up and read down policy, and you start with a secure state where everything is read down and write up. And then you have, some transactions. People create files and people access files, read and write transactions. Each transaction would follow the policy of BLP. Then the next state is also secure, and then the following state is secure. And so that's basically the basic concept, and it try to reduce the amount of people who can access information. And of course, if you think about it, it may not be very realistic, because the good example that I keep using is that if the general want to ask a soldier to get him some fries and a Coke, and then this won't work, because that would require the general to write a text message to the soldier, and then however the general say having top secret clearance, so should never write anything of unclassified nature or a lower security label, having lower security label, and so he will never be able to communicate anything to the soldier, not getting his fries. BIBA integrity model. This is usually always considered as a dual. BIBA is very important. It's an integrity model, and we talked about integrity means preventing data corruption. BLP is a confidentiality model preventing data leak. So interestingly, BIBA policy is completely opposite. Read up and write down. Okay, so this time the general will be able to send an email to the soldier to get his lunch. Okay, and the read up means that you can the soldier will be able to access information of higher privileges, but the soldier will not be able to modify any information with a higher privilege. Suppose that in a different scenario where you have the military general wrote a document, and then the soldier need to proofread it. Okay, at this time, the BIBA model would disallow the soldier from touching the file, from modifying anything in the file, for fearing the soldier messing up the file, destroying the integrity of the file, because the file will have a high top secret or very high security clearance, and the soldier only have a lower clearance and won't be able to write to an upper level. And so the complete opposite. If you have both models, you're doomed. You cannot do anything. But a little bit more about the BIBA integrity model. You have again, subject cannot corrupt data in a higher level, and then subject cannot be corrupted by data at a lower level. Okay, so in essentially what we have just described, and here a little bit formal notification representation, and it's read up and write down. So are these two models too strict to be useful in practice? And I believe they could be they were useful in some scenarios back in the 80s. But like we described, the civilian email system, this would not be very usable. The email system, of course, in the civilian system, we don't have clearance. We don't have multi-level security. Everyone can email everyone else, and of course, the models just cannot work. But then if you say, okay, the technical staff, you already have root privileges of our servers. Maybe they have higher privilege, but you can still write email to them, right? So so in modern system, usability is the biggest thing. It's the highest priority. You want to get things done as opposed to security. None of the models is useful here. We'll come back to BLP a little bit later in a more experimental setting. More traditional OS concept, discretionary access control. Mac is where the system, like the system admin, would specify who can access what file. But the modern OS is all following the DAC, discretionary access control, where the data owner specify who can access that file. And we talk about the models. Clark-Wilson is a different model that talks about separation of duty when you have transactions. We'll not talk about this. Did people use BLP model for security in practice? Interestingly, the Frank-Cohen paper we keep mentioning did use BLP for experiments. Again, recall that paper talks about different undecidability problems. And in addition, it also talks about ways for us to make sure viruses are blocked, are isolated. And so BLP model is at that time, back in the 80s, used in some systems. So the experiments, the authors did an experiment on a BLP system. And I remember the paper mentioned it's very difficult to actually access such a machine, learn how to use this machine. And then it's just, even for simple experiment, it took him a long time to set it up. And so, and UNIVAC is the name of the machine that they tested. It has had a BLP access control implemented. And of course, they demonstrate that the virus gets propagated a lot. And part of the reason is because BLP allow you to write up. So if you have a soldier whose files is infected, and then because BLP allow you to write up, and the infected file would propagate to secret, top secret levels. And so the paper also point out that if you have a BIBA model, that will make it easier for you to restrict the propagation of virus, because BIBA prevents you from write up. So if you write, you can only write down. And so in that case, unclassified files would not be able to infect the top secret files. Right. So because that will involve write up. So that's an interesting interesting observation. Of course, it's very intuitive. Nowadays, we don't really have any BLP or BIBA implemented on any of the systems, and because of the discretionary access control, it's pretty flexible in terms of read and write. More on OS security, there's a free book written by my collaborator Trent Jager from Penn State. It's called OS Security. It's free access. Make sure you use VPN. It is free access, but you have to go from Virginia Tech. Some of the common concepts I want to say a little bit here is, the OS runs operating system, okay, not the security part, the OS, what's the purpose of OS? It manages system resources, making sure the processes will be able to access system resources because it's all shared, right? So you have like 40 programs running on your program. You only have one memory, one disk, one printer, one, like several network interface. And so they have to share. And so this sharing requires scheduling policies, access control, and so on. And so some of the concepts that repeatedly came up from OS discussion, one is called the reference monitor. Reference monitor usually refers to you have a mechanism in place in the OS that will be able to apply access control policies. Okay, and so because you are able to monitor, right? You have to intercept certain calls and then say, okay, is this allowed or is this not allowed? Another concept is called trusted computing base, and the TPM, SGX are both trusted computing base, but it doesn't have to be hardware based. It could be a software microkernel, that means really, really small critical component of the kernel, a smaller kernel within a larger OS is assumed to be secure, and you have different ways of making sure it's secure. So it's just a root of trust. In a lot of times that when we talk about access control, enforcement, authorization, that involves subject, an object, and then operation, okay? And so you decide, can the subject access the object in this operation, read, write, execution, and so on. Subject is usually user, process, and so on, and then object could be files, the network sockets, and of course the policies are up to you, up to the specific scenario. Scalability is one challenge. You can have all kinds of hooks where you observe system calls, intercept, logging. But then if you stop them too much, your system would slow down big time. And so you have to be careful when you place those reference monitor hooks. Hooks allow you to take a peek of the transactions, the execution. And so you can place a hook for intercepting system calls, function calls, library calls. Reference monitor, there's no like single solution for reference monitor. It's just a concept. Okay, it's a concept, and then you can have your own implementations. And then you will apply certain policies based on the particular scenario. One of the, so you will see a lots of like access control in the system level research solutions that talks about who can access what. And then there is always performance, scalability is always one challenge. Another concept that usually come up is a race condition, which is a security vulnerability, and there's different flavors of race conditions. One of it is called TIMO check to time of use. For short is TOC-TO. TOC-TO, and here is an example. You have, because when you check and when you use may not be an atomic condition operation. So that means may not be just one operation. It should. A better way of doing this is when you check and then you use, it's just one system interrupt. But here, if it's split, say you have a mail server checks for whether a file exists or so on, do some checking and then decide to append a new message, and that operation may be executed under root privilege. But then during the small gap, and this got to be really, really small time window. And but then in this small time window, attacker may be able to point to you create a symbolic link and then switch from a mailbox to a password file. Okay, so it in this case, and this is just done outside the send mail, and you can write some script. Attacker can write a script that basically do this symbolic link repetitively, like the infinite loop, and then you will be, if send mail is vulnerable, be able to take advantage of this small window. And then what end up happening is that the attacker will be able to gain the root access and then be able to open password file and do all kinds of other things. And because the original mailbox has the attacker's privilege, and so things get switched. And here is another example. You have you want to get the status of the file, and then if the status is okay, you open the file. But then at this point, the attacker may be able, outside the victim computer, outside the victim program, create a symbolic link, and so at this time you are not open the file. You open something that's being pointed to that file. In that case, it's a password file. So, and a lot of the suggestions is, of course, make this operations atomic operation, so that you just don't create this short time window. There's some more explanation from chapter 2 of the book, and then on this blog post, very useful. I recommend you to all read it. LSM, additional concept, Linux has this Linux security module, and it's a framework you can implement different policies, and one of the policies, different policy, different models, and the SE Linux is a mandatory access control model that can work under LSM. And so you can have very, very fine-grained specifications saying which process can access what call. And so if you want, that can be specified with LSM framework and SE Linux. And of course, we're not talking about usability. A lot of those access control framework, in particular SE Linux, has very high entrance level, and the learning curve is pretty steep. And I'll be amiss if I don't mention anything about Android OS. So Android mobile device has its own special operating system. It's built on top of Linux, but then each application has a virtual machine called the Dalvik virtual machine. I think of it like a sandbox. It has a unique Unix UID. And so you have seen a lot of the permissions, right? So if you have an Android phone or an iPhone, you will ask, do you allow access? Do you allow this app to access your location? So on. And so the camera, Bluetooth, and so on, those are protected resources, and they have protected APIs, and only the app, by default, the app would not be able to access to them. And only when it will say in what is called a manifest file, the app's manifest file say, this is a phone app, and therefore I need to access telephone function, SMS function. And so it's this is called permission, okay? And then you can also request a permission to ask another app to make a phone for you. For example, a map app You can find a restaurant on a map, and then there's a phone number. When you click, it will use a different app. And then that request is sent over to a different app to make the phone call. And so the permission is the most distinct feature in Android operating system. And of course, the virtual machine, the Dalvik VM. Android apps are all written in Java. And there's a lot of remote reverse engineering tools. And so last time we talked about VirusTotal, and a lot of Android apps and analysis tools. Android 6.01 and higher, they now require runtime permissions. Runtime permission is, in contrast to static permission. Static is where, when the app gets installed, it get all these permissions by looking at the manifest files. So runtime, the biggest change is that it asks the user, when the app gets installed and is running for the first time, it asks the user, do you allow? Most of the time that it only asks the user once, otherwise it will be a little bit annoying. So the user can choose to allow or deny. And in general, the mobile OS works extremely well and also very useful. And of course, if you from a non-technical savvy user's perspective, this is sufficient. We haven't looked into, our group haven't really looked into the OS security in Android, but then literature seems to have good. The security seems to be well designed, and then because it's a newer operating system, and the researchers will be able, the designers had the opportunity to have a lot of built-in, isolation, partition, virtual VM, and security features built into the design of Android OS. And in addition, because the mobile device has far faster and faster computational power, and so you can afford to have those higher level of separation, making sure that this app will not impact the other app. If this is corrupted, it will not be able to do much. Code signing, before we go, I want to say a little bit about code signing. So we talked about the PKI, right? Everyone has a public-private key pair, and then use the public key. You can get public key certified. And so you can also use a key to certify the code that you produce, just to show that, this is, if you trust me, you trust the code. So this is the basic concept of code signing. If you trust Microsoft, then Microsoft would give you the code as well as a signature that goes with the code. And then the signature can be verified, and if you trust the Microsoft's the certificate, right? The certificate again is signed by a CA, and would just bind the certificate is to bind Microsoft's public key with Microsoft's name. Then you see, oh, this code is this indeed come from Microsoft, and I do trust it. And so the concept is very simple. As long as Microsoft keep its secret key safely, securely, then no one can forge code coming from Microsoft. And so this in general it works very well, and a lot of the code signing is already in place. And you don't see it, but the browser, the operating system use this in a lot of scenarios. One of the disaster that involves code signing is in Stuxnet, and we mentioned this already. Two Taiwan-based semiconductor manufacturers, and they got their private keys compromised. And so the code coming from malicious attackers are actually signed with their private key, with J Micron, and this one is Realtek private key, and then gets actually installed on the NE Siemens system in the nuclear condensation plants. So, and afterwards, these certificates were quickly revoked by Verizon, and who had issued and then the manufacturer, semiconductor manufacturers, came up with new keys and get signed by Verizon. So extremely important to keep your private keys safe, especially the private keys are used to generate code signing signatures. And so if you know, like after you graduate from here and then you're asked to secure some private keys, okay, how would you do it? So, so here are some best practices for code signing recommended by Microsoft. You use special hardware to store private keys, and TPM has this feature that would not decrypt the key if OS is compromised. Would only decrypt the key when the hash values get matched. And so you also use a test signing environment. In the test signing environment, you don't use your real key, use a self-signing key. And only when at the very end, the private key is used. Otherwise, if you have to use the real private key here and there, you know, I need to test my system, I need to test my system, the keys will be scattered everywhere. That's not a good idea. And so here is an example how where else can you go? Things can go wrong when you do code signing. We said that the keys could be compromised. Here is an example where it shows that okay, you may still you know, code implementation is also very important. You know, when you think about code signing, okay, I sign my key, okay. But then when you actually verify the signatures, you have to be careful. What lines in this code is wrong? And you see we have 2 if and then nested. We have 3 if and then well, we have 4 if. But then the main thing is the nested for loop. Nested for loop. This code is for verifying digital signatures, okay? The problem is these few lines. The digital certificates came with a chain. It's not always a chain, but most likely it has more than one signature. Because there could be the root CA signs, the secondary CA signs, the tertiary CA signs Microsoft, and then Microsoft signs the code. So you have a whole bunch of signatures, and then you have to verify all of them, not just one of them, and that's what this code is problematic. It only verifies it verifies all the signature, but then it's break out the loop when at least one signature is verified. You have to verify all of them, not just one. It's conjunction, okay, not just disjunction. So needless to say, that was just one example of implementation issues and illustrating the gap between theory and practice. And in general, code signing is becoming more and more of an industry practice, a standard. And because we have the PKI in place, why not use it for all kinds of critical things? You know, when you have updates, right? Software updates. The software updates has to be signed, right? So, as a matter of fact, if you're still looking for class project, would be interesting to do something about code signing like I would say, understanding how cosigning practice currently is, and then maybe to see how well it's implemented, how pervasive there is for mobile devices or regular OS and so on, and then ways to improve them. So I believe this is the last slide, and that's it. Oh yes, if you have looking for class projects, how to help developers write secure code. We recently gave Java crypto coding tutorial. You feel free to check it out. And there's different ways for you to contribute, and again, closing the gap between theory and practice in cybersecurity. All right, that's it. Thank you so much.